So last time we embarked on this first activity to look at linked mechanisms, and the first one was linking flow in dual porosity media, where we could write, for instance, flow in two separate meshes, basically, which were not connected at all, but were superimposed on each other. And we could use one mesh to represent the flow within the fracture network, and the other one to represent flow within the porous medium. And they're completely unlinked, but we talked about how we would actually put them together to be able to make them talk to each other. So today we'll actually look at, instead of just flow systems, a mechanism of making perhaps the type or the typical geomechanics behavior, pore mechanics, to work. And we have the individual components that allow us to do that. And so pore mechanics is basically the idea of consolidation. And so consolidation, I always broach the idea of thinking about it in terms of a sponge. But if you take a sponge and you compress it, then you squeeze the fluid out of it. If you happen to put a membrane around it so the fluid couldn't escape, then as you compress the sponge, you'd actually build up pore fluid pressures within the sponge. And those pore pressures would be something that, since mechanical behavior is related to effective stresses, those large stresses and high pore pressures would be something that could potentially bring it to failure. And so it's an important system from that regard. And so we have the basic components to be able to deal with this. You could think of it in the same way as we talked about flow problems in dual porosity media, in that you could imagine having a mesh to represent the solid mechanics part, the deformation part, and you could have a mesh that would represent the flow part, and individually those would not necessarily talk to each other. So we know that the systems that we would deal with would be something like, for solid mechanics, it would be F equals Ku. And for the flow part, it would be Q is equal to K, we'll use pressure rather than head, plus a time derivative of pressure. And these are all submatrices. And if you look at these individually, then in terms of what they would populate here, if we just divided through, took the time derivative of this equation, so divided through by delta t basically, we get a rate of change of force and a rate of change of displacement. And so these individual terms that we have here, this k term here would be this term. This would be k in this. I suppose we should call this something like k fluid. This k term that we have here, if I use different colors, that operates on pressure would be this, kf, say. And we'd have one other term, which would be the storage term, which operates on rates of changes of pressure, which would be this term here. And so this would be the individual components that we have here. And of course, what we've referred to as the load vectors, the parts here, would be these parts. And these would be the variables that they operate on. They only operate on these first two components, pressures and displacements, And so that would be our two individual systems that have no communication with each other. If we want to talk them to each other, in other words, we want the fluid pressure changes in one system to give some impact on the solid mechanics expression, then we need this term. And what we'll find out is that because this expression has to be written in terms of all apples or oranges, the apples have to be units of force. This is units of rates of change of force per unit time. Then this has to be also a force per unit time that results from the product of this times the pressure. And so this term here we can think of as a body force that adds into it the effects of the fluid pressures as a body force, which the solid mechanics expression, really an equilibrium equation, can accommodate. So that's the first part. And so the other part is that to talk to the fluid equation so that displacements have some influence on the flow equation, then there has to be also this cross-coupling term. And we could think of this as in terms of the definition of this has to be a flow rate. So a flow rate would be, this would be in meters cubed per second by definition. This would be in newtons per second. Yeah, it is newtons per second, but it's also a body force. But this would be in terms of a volume change per unit time. And so you could think about it, if you're taking a sponge and squeezing it, it's the amount of volume of fluid that you're able to squeeze out, or that you're producing, that you have to get out of the system per unit time. And so this is a volume flow rate. And so I think the only important pieces of information to recall are that it's these off-diagonal terms are the only ones we haven't seen so far, and they have a physical meaning, a body force and a rate of change of volume with time. And because they have to be congruent with the units of those individual equations. And you remember also that these individual equations come from this conservation equation for this second one, for the flow equation, is that volume in equals volume out plus accumulation by definition. That's our conservation equation. And this equation is F equals ma. So this is F equals ma. So in other words, sum of forces have to equal each other, and if they don't, then there's some acceleration taking place. We have no accelerations in our system, so this is actually just equal to 0. So it's just, this is a force balance equation for the top one with appropriate things thrown into it, and this is a mass balance equation for the second one with the appropriate constitutive relationship in it. So it's important to be able to back up and see that. So what we'll do today, now that we've kind of introduced that, is we'll talk about this coupling between hydraulic behavior and mechanical behavior, which is the essence of what we're trying to do, often referred to as pore mechanics. And what the first thing that we'll see is that we've talked already about having a number of requirements for the solid behavior that we have. And we said that those requirements are, we have a continuity equation, a conservation equation, we have a constitutive equation, we say that displacements or pressures are continuous, and we have boundary conditions and initial conditions. That's the four requirements we've talked about that define any solid mechanics, or any mechanics problem, really. And so you'll recall that when we talked about our constitutive equation, we always linked stresses for the solid mechanics part to strains through Hooke's law. What we never defined was that the stresses that we link to strains are actually what we would refer to as effective stresses, which we'll call sigma prime. And so these are effective stresses. So in other words, effective stresses require that we know what the magnitudes of fluid pressure are, because once you subtract out the effect of those fluid pressures, the effective stress that's left is just the magnitudes of the intergranular forces. And so the basic of polar mechanics really is understanding what the role of effective stresses are. And we can develop finite element equations for those. These summary equations can also be cast in some kind of partial differential equations, PDEs, which is useful for us as well, but we won't focus on that. And then we can implement these finite element equations in one of two ways. We could directly implement them using the finite element equations that we've developed in EGE-FEM. Or, as COMSOL works, we could also implement them directly using the PDEs in COMSOL. And so the implementation is slightly different depending on those two things. And we'll talk about both of them. Maybe not all today, but ultimately we will. Okay, so that's the picture. So let's get started on looking at what polar mechanics is. The idea is basically this, is that you can take an assemblage of grains. Around those grains you have fluid, which exists in the pore space. And when you apply the load to this assemblage of grains, physically what you can imagine happening is that the forces that are transmitted through this will really pass through the intergranular contact. So if you imagine these as kind of, I suppose you could call them force chains or force trajectories, and these little lines that go through here, you see that they go through the individual grain-grain contacts. And so that is what carries the load through the system. If you have a fluid pressure that's acting within the pore space, we'll just call it P, then you can imagine that the forces that are acting against this force that's being applied on this portion of the boundary where there's just pore spaces is something that alleviates, is pushing back against the forces that are applying. So in other words, it reduces, if you like, the magnitudes of the intergranular forces that can develop. And so that is embodied in this idea of what's referred to as Terzaghi effective stress. And the terminology we use is that the total stress is equal to the effective stress plus the pore fluid pressure, just written out. And so the stresses, of course, are a tensorial quantity. And so they're not single valued, but they're actually a matrix. And so if we wrote these out for this, it would be something like this. Pressures are scalar values. M would be just a vector of coefficients, ones and zeros, or it could be numbers different from that. For those of you who know something about this, might also have seen this law as written in terms of total stresses equal effective stresses plus a coefficient times fluid pressure. This is referred to as the BO coefficient. And it's just a number between, typically, well, not typically, between 0 and 1. 1 if it's a big effective stresses. If it's equal to 0, then effective stresses have no influence whatsoever in the deformation process. And so it's the crux of what we're dealing with is that we define effective stresses because effective stresses control two things. They control deformation because effective stresses are equal to Hooke's law multiplied by strains. We've never defined this before because we've never used fluid pressures. And they also define failure. And so, but whatever that would be. But total stresses, running out of space, so I'll just move it up. But total stresses define equilibrium. So in other words, they describe sum of forces are equal to mass times acceleration, and if accelerations are 0, then this is equal to 0. But the stresses that go into defining this finite element statement or equilibrium statement have to be the total stresses that are applied to the system not the intergranular stresses that are felt inside here. And so that's the reason we have to now define effective stresses, because they define deformation, but the finite element equations that we have are written in terms of equilibrium, in terms of total stresses. So we need to be able to define exactly what the relationship is. So our approach is this. So we want to be able to solve the system equation, so we divide it into two parts. We have the solid mechanics part, which we'll deal with first, and the fluid mechanics part, which we'll deal with afterwards. The solid mechanics part, the derivation would be exactly the same as we've done for solid mechanics, with the modification that when we talk about total stresses in our system, we write them in terms of effective stresses. We can write them as total stresses being equal to effective stresses plus fluid pressures. We can also write them in terms of small changes in these magnitudes, which is really what this delta refers to. And if we aren't writing them for just one component, so if they had sigma x, sorry, I didn't write this. This is effective stress, of course. If this was just one component of stresses, this would be fine. But if we want to write them for all the components that we have in our system, then these have indeed to be vectors. And if we're adding vectors to each other, we have to have something else that allows this scalar value to be mapped onto a vector as well. And so the relationship for Terzaghi's effective stress for a two-dimensional case, and I'll just zip up to this, in other words, where we have stresses in the x direction and the y direction, and also a fluid pressure in the system, would be that we'd have these three components. We have stress in the x, stress in the y, and a shear stress. So this is tau xy. So in other words, on our little cube, it would look like this. Sigma y, sigma x, and tau xy, which we're just writing as sigma xy here. And so we have these three components. They map onto three components of effective stresses, but because the fluid pressures are a scalar, we have to have some convenient vector to map these. And so it's one that contains two values of 1, and because effective stresses or fluid pressures don't act on shear stresses, then this value is just 0. If we wanted to have this value of BO coefficient also thrown in there, which might be not equal to 1, then we could just pre-multiply this by that value as well. Or these values could be 1, alpha instead of 1. So that's the one piece of information we need to be able to do this. The reason we do it is because the constitutive law is written in terms of effective stresses. Let's, instead of using D for the constitutive law, write it as Hooke's law in terms of modulus. It'd be the same as we had before for plane strain or plane stresses. And so this. And then what we could do, because we've made the case that the equilibrium equations is written in terms of total stress. Then what we could do is we could merely replace this value of the effective stress here as with this. So this here is this. If we substitute this into, I guess, into here, we end up with this expression here. So all we've done is taken the component which is due to effective stress and substitute it by a strain and Hooke's law, which we know how to get. So the reason we want to write this in terms of total stresses is because of this. Equilibrium requires that. We've never really talked about equilibrium before, but if you did look at the videos for solid mechanics, then the derivation for the finite element statement was using the principle of virtual work. And the principle of virtual work is written, I guess, in microcosm here. It says that the internal virtual work and the external virtual work are the same. The prop I always use is this to be able to describe that. So the external virtual work would be the forces that we'd apply that would go through some displacement as you load it. And so the external virtual work would be the force that you apply multiplied by the displacement that it goes through. Constant force multiplied by a small virtual displacement. By definition, force times displacement is Newton meters, which is work, and so it's work. As you squeeze it at the boundary, all of the interior parts of this conform to that deformation also. So you get strains on the interior, and those strains get put through the forces that are already being applied within the interior. They're not discrete because maybe on the boundaries at the nodes we only have forces at the nodes, so the product of the force times its displacement is a discrete magnitude. But the strains are everywhere throughout here, and so at each point there'll be some magnitude of an applied strain and multiplied by the stress that's already applied. It goes through the strain because it's deforming and it has a stress already applied. So there's a piece of virtual work done at each individual portion of this. It's not discrete, but if we integrate it over the total volume, then it comes up with the total sum of all the internal virtual work that we have. So that's the statement for this. If we then define what strain is, we know that strain in terms of finite element equations is equal to our A matrix multiplied by nodal displacements. That's just one of our deformations. These are the derivatives of the shape functions, you remember, right? And so if we substitute for this here, we have this. If we then manipulate this by realizing that the transpose of two matrices summed together is the transpose of the individual matrix reversed. This is just a standard result. And this is basically our the precursor to the result we have. So what we would do now, if we're trying to derive the finite element equations, is we put Darcy's law in here because we know that, not Darcy's law, Hooke's law, because we know that this is equal to d epsilon, and we know that epsilon is equal to AU. And so once we put these two in here, we'd end up with this. We'd be able to get rid of the displacements on each side, and we have force is equal to displacement multiplied by A transpose dA, our stiffness matrix. So that's how we did it. So we never stopped that process halfway through, but if we stop at this point right now, and if we then just get rid of this part here and this part here, then we have a relationship which says that forces are equal to stresses, the derivatives of the shape functions, and this. This actual statement is the same as F equals sum of forces equals mass times acceleration, which in our case is equal to 0. And so we never stopped it here, but we could take this relationship that we have here, which was exactly what we're going to do, and you see it written out below, just as A transpose sigma time is equal to force. A transpose d sigma is equal to change in force. So this is this is basically what's referred to as an equilibrium condition. And if any of you have had a solid mechanics course before, then you'd recognize this equilibrium equation, I'm just skipping ahead, as something that looks like this. This is its differential form. This is saying that all the forces are in equilibrium because they're applied as stresses, both as normal stresses and shear stresses, and we don't have any acceleration. So it's basically a statement of that equation in finite element format. It's not important that we understand that, but I think it's maybe a curiosity. And so this is the equilibrium equation. We know what this is. I'm going to write this as uppercase A, just to make the distinction that this is the A matrix for solid mechanics. It's the derivative of the shape functions. It's different from the A matrix for fluid mechanics, right? Because one is 3 by 6 and the other one is 2 by 3. They're different sizes. So we have to make that distinction. We have this here, and we also have this here. So presumably we can substitute this into here. And if we do that, then equation 5 with the constitutive law thrown in, and importantly with the constitutive law written in terms of total stresses, but including the impact of effective stresses and pore fluid pressures. Now we have an equilibrium equation which includes total stresses, but now it includes the influence of effective stresses and pore fluid pressures. And so this becomes equation 6. And so what we would have would be, after we make this substitution here, we end up with a part which includes this. In other words, this part here is this, because I guess we could write this as d epsilon is equal to a du, right? If we substitute here, and then we substitute in here, so this is this term here, and u goes outside this term. So this term is the first part, which is from this, and if we substitute this, A transpose multiplied by MdP is this term here. And so I guess that's, I didn't need to draw it up there because I've talked about it right here. And so that's what that is. And so that's our finite element statement. If you look at what the individual terms are, this looks hopefully similar to something that we've seen before. This is our stiffness matrix, what we called before uppercase K, underbar. And so it would be this term here, operates on displacements. And the other term would be something that operates here on fluid pressures. And so if we zip down to that, indeed we have that. It operates on fluid pressures. Originally this is in terms of displacements, fluid pressures and forces. We think we want the terms in terms of rates of changes of those. So we'll just take the time derivatives of those, which is what has initiated these. And this is the second equation, which would be this term, which was, what was it? S12, was it? Or something? Previous thing. S12, this term here. And so by definition, we can check that you could check that we're adding apples to apples and oranges to oranges. It'll work out that's the case, but this is now the appropriate relationship that defines that behavior. If we wanted to simplify it in terms of just a matrix equation, then this would be the stiffness matrix. This would be this term that represents a body force once it's multiplied out, and they have to be all uniformly defined in terms of forces per unit volume per unit time because of this. So that's the first of the relationships. So we have that. The other relationship we have is due to conservation of mass, and we can do it in the same way, but we'll write things maybe slightly differently. So we need to solve two things. We need a conservation equation, we need a constitutive equation, we need fluid pressures to be continuous, we don't have to enforce that, and we need to apply boundary conditions. So the two main conditions we have is a continuity equation, conservation equation rather, and a constitutive equation. Constitutive equation we can think of as Darcy's law. So this is just velocity is equal to k over mu dp dx in the x direction, and we can write it for that. We can ignore the body force term because we're interested in changes, so let's just ignore those things to make our life easier. Don't need to worry about that. And so we can write this in terms of the del operator. So this would be in terms of del would just be equal to d dx and d dy in this particular two-dimensional case. That's what this term is here, operating on this. Permeability, viscosity. Conservation equation we're going to write slightly differently. I guess we could write it out if you take this del operator and operate on velocities. So this would be, in terms of longhand, this would be d dx dy multiplied on velocity in the x direction, velocity in the y direction, would be equal to 1. Is it a different, yeah, slightly different m equation, I guess. 1 operating on epsilon x and epsilon y minus porosity over bulk modulus of the fluid multiplied by the rate of change of fluid pressure. And I won't, so those are the individual terms. This is this matrix. If you write those out in longhand, shall you multiply this by this and this by this, you get, so in terms of this, this would be the continuity equation. We would just change in velocity in the x direction with x plus change in the velocity in the y direction with y, which is our standard continuity term, usually equals 0. But in this case, it doesn't equal 0. It equals epsilon x plus epsilon y, just from this term here, which is actually the volume strain, minus porosity times the bulk modulus of the fluid times the rate of change of pressure with time. And so you can think of this. This is, the left-hand side is volume in equals volume out. If that's satisfied, then it equals 0. But if volume in doesn't equal volume out, then there's a net change in volume. And that change in volume can come from two sources. It can either come from the fact that you're squeezing this and changing the strain, and if you squeeze it by a certain amount, that volume change that you squeezed it by has to be the same amount of fluid that comes out of it, which is this term here, volume strain. So the volume strain per unit volume, so the volume strain is equal to the change in volume per unit volume of this, and it's the amount of fluid that it tries to squeeze out. And the other term would be the change in the volume of the fluid as a function of pressure. And so the easiest way to understand that is if you take a can and you fill that can with fluid and it's at some pressure, and then you increase the pressure of that fluid, then all of a sudden the fluid will compress. If the fluid compresses, then it will be now smaller than the size of that can. And for the can to still remain full, it has to suck some fluid in from the outside, which is the volume change that you get. And so you get two sources of volume change. You get one because the sponge is compacting and the solid grains are rearranging themselves, so there's less internal volume. There's still the same amount of solid in there, essentially, but because the grains are now more efficiently arranged, you've changed the volume of the system. And if you want to keep the same amount of fluid in there, then you have to allow some to come out. And that occurs with no change in fluid pressure. And so, so the two things you can think of, squeezing the sponge with no change in fluid pressure, fluid has to come out. There's a change in the volume. The converse is changing the pressure of the sponge but not allowing the volume to change, in which case there has to be an inflow of water to be able to keep the volume constant. So these are the two sources of the volume change within the system. Changes in volume under constant pressure and changes in volume under a change in pressure. Okay, so this continuity part on the left-hand side is what Darcy's law can contribute to, because we have values for each of these terms. And so if you substitute 9 into 10, written in this way, you end up with this expression here. So the continuity term on the left-hand side now becomes this. This term, if we ignore this again, just becomes something like d2p dx squared plus d2p dy squared. all multiplied by permeability and viscosity. That's what this term is. And this is equal to these two individual terms, which I won't write out in longhand because we've just described it in excruciating detail maybe. So the compaction due to squeezing it, and also the compressibility of the fluid. And so what else do we need to do? So this is our final equation that we have with these two sources. You remember that when we do make a finite element state from this, what we do is we say that this expression has to be absolutely correct always. So what we could do is we could take each of these parts and write minus and plus and equals 0. So in other words, this expression is equal to 0. If we multiply this whole expression by some other number, such as a weighting function, it's still true, right? No matter what this is. And if we evaluate it everywhere within the region that we want to calculate it, then it's still true. And so the Galerkin approximation is just that. We take this relationship, which is in these brackets, which is equal to 0. We multiply it by a weighting function, which is our term here. We say it's true everywhere within the medium, and so it's a two-dimensional medium in our particular case, and so it has a particular area, and the integration is with respect to x and y. And this is our finite element statement once we do some substitutions. The substitutions we do are what? This magnitude of pressure that we have here is actually equal to what? The pressure is going to be equal to a shape function multiplied by nodal values of pressure, which we can substitute for this. In other words, this term here. And I guess also these are strains, so we know that strains are equal to our solid mechanics A term multiplied by nodal displacements. So these are strains at a point. It's a vector because there's strains in x, y, and shear strains. There's 3 components. And these are nodal values of displacements. If we want to know how they change with time, we can just differentiate them with respect to time. And that becomes this term here, right? So we just substitute for these. That's all we've done. And finally, I guess this would be the same. We know that fluid pressures are equal to, these fluid pressures here. Fluid pressures are equal to nodal values of fluid pressures multiplied by the shape functions. If we want rates of changes of those fluid pressures, we just do that. And we have this term here. So in other words, we make this substitution that this here is equal to this. So we've made substitutions for continuous values of pressures and strains, which are continuous in the system, to ones that are determined in terms of displacements at the nodal nodes of our elements and pressures at the nodes of the elements, and we've made this substitution in here. And so once we've made those substitutions, this equation 15 is the final expression. And so we could write this as, in terms of our own terminology, I think we called this previously Kf multiplied by nodal values of fluid pressures. So this is this. This is our conductance matrix, finite element conductance matrix. We have 2 other terms, which we've referred to as, this one here is what we've referred to as S21. It's the coupling term. And let's not go there yet. Let's do the other one. This one here is the other coupling term, which we've called S22. I don't think I can have everything on the same screen at the same time, but just let's remind ourselves. It's this second equation that we're trying to put together. There's portions which relate to Darcy's law. So this is what we've just defined as K sub F in our previous 2 pages down. And these are the 2 other parts. One which operates on displacements, which is the coupling term, and the other one which operates on fluid pressures, which is the same as our storage term from previous, right, when we did groundwater flow equations, this term. So in other words, this term here would be S22 that exists here. And in this flow equation, S21 doesn't exist. So the question is, S21, where the hell is it? It doesn't exist. And so that's the term that we've added. So this is the expression we're trying to get. So let's go back to where we were. And let's just confirm exactly what these things are. And so if we wrote this out in longhand, this would be this term here, which is S22 bing times P dot. I guess it's a minus in this particular case, but let's not allow that to get in the way. And S21 multiplied by U dot is equal to Q. And so if we wrote that in the terminology of what we had before, remember that our flow equations look just like this. Kf P plus S P dot equals Q. Right? This is the Fe equation for flow. Flow only. So what we've done is we've added an extra term, which is this. And of course, this is our storage matrix. Remember this? B transpose B integrated over volume is just, if you can condense all the individual terms of that matrix, it's just the volume of that element. So that's no different from this. So the only new term we have is this. And this is our coupling matrix. And it's, I guess we can look at what the individual components are. These are the shape functions. The shape functions are the same for the solid mechanics and the flow elements. This is just, M transpose is just a matrix of ones and ones, just ones in this particular case. Ones and zeros. Because we have shear strains which don't contribute. And so the one thing I didn't add in here, plus 0 times shear strains, because there are 3 strains that are involved. And so M transpose is, if we wrote it out in longhand, 1, 0 multiplied by epsilon x, epsilon y, and gamma xy. And so the fact that there's no volume change that results from shear strains is evident if you think about what they are. I don't have a pack of cards on me, but if you take a pack of cards and you scoot them over so that instead of being vertically aligned, they're 45 degrees. So in other words, you take a pack of cards that looks like this, that has all the laminae like here, and you do this, then there's been no net volume change. This volume here is exactly the same as this volume here. And so when you apply shear stresses, there's no net volume change in a linear elastic system as a function of that. And so that's the reason that this term here, in the same way that when we look at effective stresses, shear stresses aren't operated on by fluid pressures, shear strains don't cause a net volume change, and so this 0 is appropriate there. And so if we dissect this term that allows us to get this volume change, it's just, this is the strain displacement matrix. We know that epsilon is equal to AU. So that's exactly what that is. These are the shape functions. So the shape functions would be that displacements, or let's say pressures, are equal to shape functions times nodal pressures. So that's what that is. And this is just this. So those are the 3 matrices. And physically, all this is saying is that if you displace this by some amount, it squeezes a certain amount of volume into the system. And it acts as a volume source that then has to be redistributed. It can be distributed in two ways. It can be distributed by flowing out of the system really quickly. If this is big, it will just dissipate. If this is not big, then the other alternative it has is it builds up pressure. So you squeeze it, pressure will go up because it can't get out quickly enough. So that's a useful way of thinking about it. So that's it. So those are the two expressions. I'm not sure whether, yeah. So if we write it in the same, so this expression here, sorry, it wasn't very well ringed. This expression here is just this. And so between this and the one on the previous page, I'm not sure what we called it, these two, if we write our matrix relationship, then we'd have something that operates on displacements and pressures. If we just write two of them, we ignore all the other terms, plus one that operates on displacement rates and rates of change of pressures, and is equal to some term. Top equation is written in terms of forces, or rates of changes of forces as we have it, and the bottom expression is written in terms of fluxes. And so we just need to find out what the individual terms that inhabit this matrix are. And it's perfectly apparent from the equation above that something operates on displacements, which would be this term here. Something operates on rates of changes of fluid pressure. Storage matrix. And this operates on fluid pressures, which would be this one. This is our conductance matrix. So in other words, here, everything without this term in this relationship would just be the flow equation, nothing more than that. If we zip up to this one up here and take this and put it in the right places, then we have something that operates on rates of change of displacements and rates of change of fluid pressures. And so it'll just go on this right-hand side as well. So was it B11? I think it was, right? Which operates on displacements. B12. All of these are submatrices, of course. And this is the stiffness matrix. And so this system alone, without this term, would just be our F equals Ku, our finite element relationship. This one here is Kp plus S P dot equals Q. So they should all be quite familiar now in terms of what these are. And these ring terms are the coupling terms. And again, just to reiterate without doing it to death, this has to be in terms of volume flux. So this is a source, if you like. So in the same way as we talked about the dual porosity systems, two overlapping media, one fractures, one matrix. They act completely independently of each other, but we allow them to talk to each other by this fluid exchange term. What goes out of one system has to come into the other system by continuity. So in this particular case, this is just a flux. So this is a flux which it's trying to squeeze out. If it squeezes it out quickly enough because the permeability is high, then there's no rate of change in pore pressure and it just drains. and it balances exactly. If the permeability is really low, then it has to change the fluid pressure to compensate. Those are the only two outlets for it. And the other term is basically a force that's applied due to the magnitude of the fluid pressures that are present in the system. And so it's a force that applies to basically compress the system. And you can define a seepage force, if you write it in a different way, seepage force is equal to a change in fluid pressure with location. And you can convince yourself that that's the case because a fluid pressure has to be written in terms of newtons per meter squared. The change has to be in terms of meters, and so this is a newton per meter cubed. In other words, a newton that's applied in a particular direction within a unit volume of the system. So in other words, if you imagine applying a force in this direction throughout this body, which is equal to this dp dx, and if you hold this body here and not allow it to move, what's going to happen? That left-hand boundary is going to stay the same, but the upstream right-hand boundary is going to compress because it has this force. You could think of it as being a body force due to self-weight. If you turn gravity on, it will compact because of the self-weight of this thing. And so this physical interpretation of this is it's a body force that's applied to move it in that way. Okay? So lots of derivations, but anyway. So if you think about it in those terms, then we can look at the expressions. So wipe your mind clean then of what we've done. So we've solved two systems of equations. Conservation of momentum is F equals ma, and continuity, conservation of mass, is that dv dx, if we write it in these terms, is equal to accumulation. And as a result of that, we have this matrix relationship. If we want to solve it, we have to get it in terms of ax equals b. Right? We know that. So we need to just solve a matrix equation. And the way we do that is to write this particular matrix equation at some particular time, tau, when it's always exact. We don't need to know this. Someone trying to get in. They've heard it's exciting in here. Is everyone still awake? And so we can write this as any particular time, and we can substitute these values, right? We said before when we dealt with this that if we look at any particular node and we look at the head change versus time, we have two different values of this at ht, and sorry, this is t plus delta t. This is just t. And that these would be the values of heads at those particular magnitudes. But these could also be displacements, or they could also be pressures. And so that's really all we're doing. We're looking at the finite derivative. So we substitute this into here. We substitute this into here. And we then manipulate it by moving the terms that we know to the right-hand side, and those we don't know we keep on the left-hand side. The terms we don't know would be this and this. And so once we've substituted into here, these are the terms that go over to the right-hand side because we know them, and the other ones stay. And if you go through that, we end up with a system of equations that looks kind of similar to the ones we've had before, where we just have this time-dependent term which exists here. And we know exactly what all of these matrices are. We choose a time step, and we know something about the initial conditions at time 0, what the displacements are, and the pore fluid pressures are. And we define these in terms of our appropriate conditions. And so I guess the only thing that's a little strange here is that certainly if we have a flow condition described, most of these Q values are 0, right? If they're internal nodes, the stuff that comes out of one element has to go into the other element. And so they equal, internal values of Q are equal to 0. But the one thing that maybe is a little strange here is what the boundary condition would be if we applied it onto the top of an element. And the boundary condition is that we have to apply a force, but we're interested in how that force changes as a function of time. So in other words, if you apply a load and you plotted that load versus time, and this is time 0, this is the first time step, this is delta t, this is 2 delta t, then initially there's no force applied here. Sometime between this, as you initiate it, all of a sudden you have to apply the force, which is equal to this. And so in other words, this would be the trajectory that this would take if it went through this point. But then once the force is applied, it's there, it doesn't go anywhere. And so the force then would be constant. So in other words, you can think about applying the force and then keeping it there. And so if you plot then the value of the derivative as a function of time, then what would it be? F dot is just going to be this term here, right? This is delta F, and this is delta T. And so the first value would be some, over this time it would be some finite magnitude, and then for all times after that it would be equal to 0. This is time also, right? And so this, what we've done before is we've applied a force and it's a magnitude and you keep it applied, and we'll still do that. But because the boundary condition here is defined in terms of a change in force with time, then the magnitude of the boundary condition would be some value initially for the first time step, and then the value after that, it would go to 0. So you could work that out. Yeah, and that's it. So that's the solution method. And so if we wanted to solve that, so I guess if we go back to where we started out from this. So what we've, just to be able to recap exactly what we've attempted to do. So we said that the only way, and this differs from anything we've talked before, is that we've talked about these two overlapping continua. When we look at the deformation part, we have to incorporate the idea that deformation is controlled by the total stress that's applied minus the fluid pressure. It's important to realize that because the equilibrium of our system, in terms of this not moving, is defined in terms of total stresses, but its deformation is defined in terms of effective stresses. So that's why we had to do that. So if we apply this to our system, we can get our finite element equation for solid mechanics written in terms of both fluid pressures and displacements. We can write an equation for the flow part, which is separate, and then we can arrange them so that they are loaded parallel from each other, but they don't interact. The way that they interact is through these other individual equations. We said before that if we wanted to apply it in a regular finite element way, kind of at a low level, if you like, rather than a high level with COMSOL. COMSOL is kind of a high level programming language. If we want to do it as a low level, then we have to do exactly what we have here in terms of the expressions that we have that define the system. And those expressions are exactly these. And so in the same way that we put together the system of equations to be able to represent B1 and B2, all of the B equations and the conductance equation, then if we put it together in a EGEFM, then what we'd have to do is make an effective stiffness matrix which is operated on by all the other terms. And this effective stiffness matrix would be this. And the individual terms of this would be present within the individual components. And so they'd look very similar. So I'm going to go back to this. I did this just before. And I think I can make this as big as I need. So this is what an element stiffness matrix would look like for this. It's from EGFM, but it's actually a PDF file of it, just captured. And so you'll remember that if we want to be able to get an expression that represents a element which happens to be a triangular element, then you know that the way we'd put that together would be in terms of the coordinate system, whereby we'd have a displacement at node 1 in the x direction, we'd have a displacement at node 1 in the y direction, and we have fluid pressure at node 1. We'd have a displacement at node 2 in the x direction, etc. And fluid pressure, etc. And so this individual element would have 3 degrees of freedom per node. It would have 3 nodes, and so it would have a total of 9 degrees of freedom. So remember when we talked about just solid mechanics, then the stiffness matrix which would describe it would have displacements x and y, x and y, and x and y, just for displacement. And really what we're doing here is we're superposing that with an element that has on it a pressure at nodes 1, 2, and 3. And so this is really what we're doing. We're taking F equals KU type element, and we're taking a Q equals K, we always call it KH, but we're going to call it KP. And we're just developing the stiffness matrices for this, and we're figuring out exactly how to link them together. And that's really what we're putting together to do this. I guess you don't have this, do I? I just thought. And to cut to the chase, I think the only big picture thing that's important here is that when we, for instance, put the system of equations together that we suggest here, the individual degrees of freedom that we would have that go into this, it's probably worthwhile doing. Well, even if it's not worthwhile, I'm going to do it, is to take is to look at what these individual expressions might look like. So let's look at the individual degrees of freedom which would be present in here for a triangular element. I think I have enough space to do it, but it would be an element that looks like this. Nodes 1 would have UX1, UY1, UX2, UY2, etc. And in this way of thinking about it, it would look something like UX1, UY1, so for node 1, UX2 and UY2 for node 2, UX3 and UY3 for node 3, and then the values of the pressures at nodes 1, 2, and 3. So I didn't do this quite large enough. And so the matrix equations that would operate on this would be these. And you know, so this would be B11, this would be B12, this would be B21, and of course the one in the smallest space is the biggest one, which I won't write out, but it's this composite one. But you know from looking at this that this in size has to be 6 by 6, and it's really just a stiffness matrix. This has to be rows and columns, so rows would be 6, and columns would be 3, and this would be 3 by 6, and this would be 3 by 3, as you can see. And so this essentially would be the stiffness matrix, no different from that, from what we had before. This would be the storage matrix. This would basically be the storage matrix, what we've called here kind of the storage matrix, but with different terms. basically, if you ignore this part here, this would be the storage matrix. Actually, yeah, ignore that. It's slightly different from the storage matrix. But it would have three terms in it. And these coupling matrices, it turns out, actually, that B12 is actually the transpose of B21. You can't, it has a chance of being that because it has the right size. The sizes are transposes, but actually they are the transpose of each other. And so since B11 is symmetric matrix and the storage matrix is symmetric, even when it has Darcy's law added to it, then this whole matrix system is also still symmetric. Kind of interesting, I think. Interesting to me, anyway. And so if you wanted to, I'm not going to go through this in any detail because I don't think we need to, but you could imagine that if we know how to make the stiffness matrix for solid mechanics, which we've called, if I look here, well, this is it here. If I make this, and if we know how to make the conductance matrix here, so now you'll recognize a couple of terms. The first is, if we go back to this, so this is the manipulated versions, but if we go back to the basic terms, we said that this matrix which operates on these terms, this is the conductance matrix. And it's got zeros in all the other locations. So if you look at this here, that's exactly what you have here. 6 by 6 zeros, 6 by 3 zeros, next line, 3 by 6 zeros. So in other words, this is all zeros. And then the term that exists here is the conductance matrix. The A matrix for the fluid flow part, so remember, integral A transpose dA dV. The integral of dV is just the area of the triangle. So this is the area of the triangle, which is this and this. And this part here is A transpose dA. So this is the conductance part. And so this is the conductance matrix that gets sent back to the main routine. And the conductance matrix and the stiffness matrix together are the parts that operate on the displacements or the pressures rather than displacement rates or rates of changes of pressures, right? So that's part. And the other part is this, where in this is the stiffness matrix, this is the storage matrix, and these are the coupling matrices. And so if we look at those, don't know why it shrinks it small again, but this is the, if you like, this is the part that operates on the rates of changes of something, in like the damping matrix, and this operates on the second derivatives, d2u dt squared type terms in the in Newton's second law, F equals ma. And if we look for this, the CL matrix, this is it here. And you see exactly that behavior. So in other words, again, we have two matrices that are split here. If I draw this, 0 is in the bottom, but this is the stiffness matrix, F equals Ku. This is the derivative of the shape functions, Hooke's law, and the transpose of derivatives. This is A transpose dA that goes here. This is, yeah, okay, this should be the term that is the storage matrix, what we call B22, which is something like porosity, stiffness of water, multiplied by B transposed B dV, right on the border. And the other thing is that you can probably see here, although I've scored through some of them, this is A transposed MB. Shape functions, this unit vector with ones and zeros in it, and the the transpose of the derivatives of shape functions, and this term here is B transpose. Stop it. Where are we? So this is M, and this is A. And you see that A transpose MB, these are the transpose of each other, and so it's symmetric on the diagonal. And so that's what we need to do to be able to put together the appropriate sets of equations to do this. So in other words, if we make a matrix, which we've called in the previous KL, and in the previous we've called CL, we calculate what these individual matrices are, you send it back to the remainder of the program, and the rest all gets done by some manipulation. But to be able to implement this coupling, you just need to be able to use what we've known before, and we've known certainly this equation, and this equation, and this equation before. All that's new today is these linkages. And so you should think about these in terms of physically what they mean. So that's fine for today. So I'll shut up now. What you might do is that there's a recorded 6.3, which rather than do it in class, because I can't get back into COMSOL 3.4, is you might look at it. I'll send you the link for you to look at it. We'll still meet on Thursday, but we'll go the next step. But what you might do in your spare time as you sit around drinking a beer in the evenings is look at that stuff, because it talks about implementing it into COMSOL. And the only point I'll make is that when we talked about introducing this, we said that the approach that we take today in developing the finite element equations is something that we can use in EGFEM. If we define the equations in terms of PDEs, then that's the mode in which COMSOL links them together. And so you can look at how that's done. It's really relatively straightforward, perhaps more straightforward than we've talked about here, in which case you need to know what the equations for consolidation are as PDEs. And so that's what's dealt with in that particular video.